next speaker, our next speaker is Santiago López de Medrano from the UNAM, National University of Mexico. He's going to talk about singularities of quadratic maps.
Okay. I want to really thank the organizers for inviting me. This has been a wonderful conference. By Monday afternoon, I had learned 4 new things. Actually, I had 4 misunderstandings that I kept in mind, and by Monday afternoon, it was all clear to me what was going on, thanks to talks with Raúl, Juanjo, and Marcos. And then in the talks, I've learned many things about which I have never thought before. So it's been wonderful for me. Okay. I gave this talk at the first Brazil-Mexico meeting in Querétaro. And speaking with Federico, we decided that not many people here were there, but finally it turned out that some people were there. So I'm going to give a brief version of that talk and then end up with some new developments. Okay, so this is the things I have been working on. Singularities of quadratic maps, homogeneous quadratic maps, and mainly interested in their zeros, the singular variety, and I've also been considering deformations given by first-degree polynomials. In the first case, usually idea is to intersect with a unit sphere and study the topology of this variety y. I will call it y all the time, except when it becomes a z, but I'll let you know. And but for this case, of course, it's not enough to consider the intersection. And for technical reasons, it is a good idea to start with the case where all the quadratic forms are in diagonal form. Diagonal. It's a very restrictive condition, but it's the one that has been studied most. And for the deformations, I really have only results where for the case where you only have a constant, no linear part. Linear part is always very difficult. Okay. So the first question number 1 is, don't we know everything about such mappings? After all, for one quadratic form, we know everything. Zero is we know when 0 is a singular, it's an isolated singularity, and so all the coefficients must be non-zero. So we have a number of positive ones, a number of negative ones. If you move, you cannot, if you don't pass through 0, you can move the coefficients as you wish, and then you can put them all to be 1 or minus 1, and without changing the topology. So you have these equations. In that quadratic form, you intersect with a unit sphere, and it's just elementary algebra to get this. And so the intersection is just a product of 2 spheres. It is not diffeomorphic or homeomorphic. When it's in this form, it is a product of 2 spheres. And in some way we can tell everything about that case. Oop, 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 oop. I need to know this. Okay, so see if that's done for if we know everything for one quadratic form, for two quadratic forms, somebody must have done it. But the only thing I have found is a paper by Wall in 1980, where he uses that to solve some questions he had about singularities, and nothing else before I started doing. In fact, these maps are two jets of mappings at points of rank 0, so these are terribly unstable. So there are things that should not appear in nature. But so the next question about has everything been done is, does anybody care about this? And it turns out that in mathematics they appear naturally. I'll go very fast, not take much time. Well, just the third one, I'm very proud of that one, because the things I've been studying have to do with quantum theories, which I don't understand, and they related to many other things, polytopes, any other topics in mathematics, and they provide interesting examples of many things in invariant dynamical systems and singularity theory, group actions, topology, and you can everything, including questions in numerical analysis, how difficult it is to solve certain type of equations. And there's now a rich theory known as toric topology. That's a big generalization of all this. It started somewhere else, not a generalization of what I did. And all this has been going on. Well, I started this about 30-something years ago, and recently, about 3 or 4 years ago, together with Vinicio, we finished understanding completely the topology of the generic case for two quadratic forms, and we know some other things about the other fibers, the deformations, the smoothings, and I will speak about all these results, including the fact that for k greater than 2, things is very bad. Okay, we start with a diagonal case. So we have two quadratic forms in diagonal form, intersection with the sphere. What one does is that one takes the pairs of the coefficients, the AI, couple AI, BI as in R2, and you start looking at, you draw them in R2 and start looking at generic convexity properties. For example, it is clear immediately clear that this intersection is not empty if and only if the origin is a convex combination of the coefficients. Any solution of this gives a convex combination. And also for the smoothness, the condition is, where's the pointer? Oh no, that's the pointer. Okay, the condition is that you draw the points, and there should be, forget about the ends for the moment. You draw the points, and the condition means that okay, the condition is that the origin should not be in any of the segments joining two of the coefficients. Okay, but this one. And again, if we deform continuously the coefficients, the topology doesn't change. For example, if we have 4 coefficients, we can always join 2 without breaking the condition, and you get a configuration of coefficients with a point with multiplicity 2. So many other cases you can do that. Put the coefficients into points of a triangle, and you can move that into an equilateral triangle, and in that case, you know this. Oh, I'm missing something. In this case, this one is as easy as the case of one quadratic form. You just manipulate the equations, and you get that the variety in the intersection is a product of 3 spheres. That disappeared somewhere in the presentation. Okay, and now the general case is you can always move the points to lie on the vertices of an regular polygon with an odd number of sides, and you take as coefficients the roots of unity, and with the different multiplicities. So you get this invariant, which is the sum of this collection of integers gives you the different cases, but of course if you rotate you get the same one. So the invariant is a cyclic partition. So you get as many cases as the cyclic partitions. The pentagonal one would be the first non-triangular, and for that you have to start doing a bit more. You take the action that it changes the sign of all the variables, and it's an action of C2 to the n, and the quotient can be seen that it's a polytope, can be thought of as a polytope, and that polytope is an invariant here, and the polytope determines completely the manifold and the action. So all the information is in that polytope. In the case we're considering, the polytope is a pentagon. It's easy to see that it's formed, the varieties obtained by reflecting the pentagon in all coordinates of spaces. So from that you can compute the Euler characteristic, and it turns out to be the surface of genus 5. Okay, and last year, that's an anachronism from Querétaro. About 4 years ago, we were able to finish the proof of this result. The variety corresponding to this partition is if L is 0, empty. If L is 1, it's the product of 3 spheres, and if it's greater than 1, it's diffeomorphic to a connected sum of products of spheres, where the dimensions can be read from the partition as follows. You have 2L plus 1 coefficients. You take L of them and you sum the multiplicities, and that's the DI going around. So we know every case. Part of this was done some 30 years ago. Some were done just a few years ago with Vinicio. And now for the non-diagonal case, we have this normal form. That's you have a diagonal part, which you assume it's the same as before, and then you have these terms. It's very easy, you just have to add these non-diagonal terms, and everyone would be like this. That's a normal form due to wall. And so we prove this case. We have all these cases when R is 0. This is that is no real part, no diagonal part. Then Y is well known that it's diffeomorphic to the unit tangent bundle. For R greater than 0, we have cases where it's a product of two spheres. We have cases where it's a connected sum as before. And so we have finally a complete description. Here are the diagonal ones we made before, and here are its products. It's a different kind of connected sum, and the only real novelty is you get the tangent bundle of the sphere. So that's the only thing a bit twisted. All the other things are very simple manifolds. They're just like surfaces, not more complicated than surfaces. Okay. And here's a bit of the proof. We have operations that give you new cases from the previous one by raising the coefficients, by adding new terms, by taking the operations on the polytope. You get, and the idea is that roughly, you have to be careful with many things, that this operation preserves connected sums. Also, we know the diagonal, the half varieties. If you have a case like this, we can consider the restrict to the subspace where one of the coefficients, one of the variables is greater than 0, like this. And in the diagonal case, it's possible to describe that. Also, these have varieties. It's the same as before. They're manifolds with boundary. They're not much more difficult, more complicated than surfaces with boundary. So it's a very simple topology. There's normal form is the same, but now you don't have a cyclic partition because you have chosen one element, one coefficient, one variable to be non-negative. So it's no longer a cyclic partition, but a classical partition. There are more cases. And I can give you the list, but I don't think it's worth it now. I can give you all the cases depending on the normal form. Depends on the normal form of the original variety and the normal form of the intersection with the x1 equals 0. And we know all of that. But for the non-diagonal ones, here when it's a z, it's a diagonal. When it's a y, it's a non-diagonal. For non-diagonals, it gets very messy, the algebraic. But okay, these manifolds are interesting. How am I doing? Oh, I'm going fast. Okay. And the deformations, the smoothings I mentioned before can be seen as the interiors of half of these manifolds. So studying this, we know also a lot about the deformations of the intersection. Okay, so what happens for more than these quadrics? Well, everything gets very complicated. Normal form, it's hard to think of a normal form because once you've put two quadratic forms in the normal form, then you have no liberty left. So all the other coefficients are kind of invariants of the system. And so the number of cases grows quadratically with the number of variables. That's a characteristic of the so-called wild problems in the theory of representations of algebras. There are the finite ones, the tame ones, and then there are the wild problems that nobody knows what to do with this, and it has a characteristic. It is easy to generalize the weak hyperbolicity hypothesis that gives the smoothness, but for extending it to the non-diagonal case, it looks bad. And there's no real good criterion to tell you if you're given k greater than 2 equations, quadratic forms, to tell if that's diagonalizable or not. So it's all kind of very messy. Even if you restrict to the diagonal ones, if you had a topological normal form, then that would be close to the classification of all the simple polytopes. That's something that the experts in polytope theory don't even mention. They don't say we don't know anything. They don't say it would be very difficult to, we would like to. There's a silence, complete silence about that. We know that every configuration of coefficients, it's a basic one with multiplicities, but that doesn't help much. And for the diagonal case, we don't have a reduction to a combinatorial problem as we had in the diagonal case with the polytope. That works okay here. Okay. I didn't mention much of the proof, but there's a connectivity theorem, there's some algebraic topology, involves computing the homology. One can compute the homology of the intersection from the polytope. Directly from the polytope you can compute all the algebraic homology. But but now we know that we get a lot of topological types, very different topological types, very complicated. All the ones I showed you were that the homology was free, and now it was proved by Bosio and Merseman that they can have any amount of torsion. If you join this with the work of Barry, Vendersky, Cohen, and Gittler, I'll mention a bit of that later, we can know now that you take any stable cohomology operation, sin root square of any degree, or secondary or any one, then this can appear non-trivially. And something that has been studied in detail is that these things, Massey triple products, which are non-stable cohomology operations, it has been shown that they're very common. That has to do with the fact that these manifolds are not formal in the sense of Sullivan theory. Okay, so about the year 2000 we were stuck there, but this wonderful thing happened. Bosio and Merseman, two French mathematicians, friends. They did a lot of work on the case k greater than 2. I mentioned something already. But they detected that there were some polytopes known to the experts on polytope theory. There's something called neighborly polytopes. The ones that appear in here are the dual ones. And they show that the cohomology ring is the same as that of the connected sum of sphere products. And they conjecture that they would be connected sums, give connected sums of these products, just as in the case k equals 2. Going back. And then there was this generalization I mentioned before of all this that gave a wide point of view for looking at all these problems, looking at them all together, and that helped a lot. And joining the ideas of Bosio and Merseman and Samat Gidler that was involved here, we were able to do more than the conjecture by Bosio and Merseman. We proved that many of these varieties are connected sums of sphere products again. When we proved it, we didn't have so clear, but in some recent work with Vinicio again, we discovered, well, it's not our result, but the result is that when you take the configuration of coefficients, the polygon with multiplicity 1, it has this property. If you join the origin to one of the points, then on each side you get the same number of points. And for higher dimensional configurations, that is the property that characterizes the dual neighborly polytopes. So the dual neighbor polytopes for us are exactly the generalization of our polygon things. And the thing is, there are many of them. Experts in polytope theory claim that claim that most polytopes are of this kind. Some by probabilistic. Okay, so let me show you what. If you take this point here will be the configuration of points corresponding to the dual neighborly polytope, and then we can start adding variables, increasing the multiplicity in any way, and for all this we get examples which are connected sums of sphere products. This one, the red one here, is the one that was conjectured by Bosio and Merseman, but for every case of that we get a big thing. And then, as I said before, there are many of these, so we can have many in every dimension. Then if you go up in the dimensions, you get some more and some more, and the number grows very much. So this is a big maze of cases that is covered by our theorem, and we can also do all the other of the operations we know and get connected sums. So we cannot tell them all, but we can tell you a big chunk of the sets of diagonal quadratic forms, and then time, yes. Then we can do again have varieties. Some cases of the diagonal one follow because you take a neighborhood of one diagonal one. All the diagonal ones will have the same topology, but it looks the non-diagonal case looks like a great unexplored territory about which we don't know very little. So we need something to get into this, to get at least a big part of the set of possibilities. For this, we have now several ideas, several constructions from classical algebraic geometry, probably use of Lie algebras, Clifford algebras. We're trying many things to try to work this part. Okay, so in the abstract, I promised a potential geometric application, and it would be this one for the case of codimension 2 embedding of a manifold in R2. The second fundamental forms gives at every point a quadratic mapping Rn into R2, and we know something about this quadratic mapping, so thinking as a topologist, I think first you take the generic cases, find out what are the generic cases, and you try to classify them topologically. Then you have to refine and take not a topological equivalence but linear equivalence, and you get something better. And then you try to do the orthogonal classifications where you get the real geometry. Well, what is done, that's one of the things I learned here, is that that's not the way it's done for the case n equals 2. For the case in n equals 2, somehow the geometers arrive at the orthogonal classification directly. That's something I have to learn. But what I said before, it's something one can do in general. Just let me give you an example. Okay, so for 2, it's well known that there are 2 regions, elliptic, which has nothing, where you see nothing, and the hyperbolic part, where at each point you see a pair of crossing lines. That corresponds to these 2 topological types, generic topological types for these mappings. But when the geometers reach this level, M5 into R7, I already know all the possibilities for the generic regions. There are all these possibilities according to the classification I have. This part is actually due to wall, just by looking at the wall normal form. But now I can tell you in any dimension what are all the possibilities. So for NM5 and R7 there will be 1, 2, 3, 7 possibilities. 8? 7. 7 possibilities, and on each one you will see a distinctive. In the tangential plane you'll see these cones of. These are the connected sums, of course, the surfaces of higher genus, and you can get 2 tori, 4 spheres, 2 spheres, 1 torus. So that's, I don't know, it's an application of a premonition of what the geometers will arrive at. Okay. But the premonition comes with a warning because the number of cases grows exponentially. So, and also from what I said, from higher codimension, I cannot give a complete list, but I can give you a lot of examples, but it's not a complete list of all the possibilities. That's kind of unthinkable to have. Okay, something I've been worrying about for a long time is where does classical singularity theory come in here? And the only possibility I saw was to have some kind of K equivalence to classify my intersections. But conversation with Raúl, I understand. Actually, in Querétaro, I made it a conjecture. We will have many examples with that give new stable maps, etc., in the spirit of matter. But now I know that's not reasonable. There are very few. There are very few that are differentiably stable. Of course, the intersection with the unit sphere is stable because everything is transversal. But I see now that the problem lies in the cone. The variety Y is stable, but the cone differentiably, you can move the differentiable type at the origin. So there are moduli. But I think there's a different thing one should try. I just been thinking this week, and I thought maybe this is what one should look at. There should be some kind of link K determinacy, meaning that if you make higher order perturbations, the intersection of the zero set with a small sphere will not change, and maybe even at zero at the origin there will be some kind of stability or determinacy depending on K. And for that my hope is that there's this work with Cidinha, Marcelo, and Shirley and me, especially directly related to this is the paper by Cidinha, but maybe we have to take into account all the ideas here. It should be helpful. Or maybe it's very easy, still don't know. Is there a theory of link K determine equivalence? Probably not. Okay, if this is true, then the deformations I mentioned obtained linear by adding just linear things would be versal in certain sense. Okay. Now there's another things that I've been doing recently that I find very exciting is to look at examples with dihedral symmetry. So more than 30 years ago, I observed that if you take the configuration of the coefficients for the case k equals 2 for two quadratic forms, they're in a polygon, and so this configuration has dihedral symmetry, and you can write the two equations as just one equation using the roots of unity. So this is a pair of real quadratic forms, but coefficients real and imaginary part. So you have this quadratic form and have symmetry. So the associated varieties and the associated polytopes, they all would have this symmetry. That was long ago, but recently we were working on trying to generalize a certain biological model So it was not biology, it was dynamical systems. So we had to do a model involving a regular polygon. And if you want to give something explicit, well, you have to look for the regular polygon. And it turned out that the equations look like this. This is a lot of equations. For k equals 2, you have the equations with the squares of the root of unity, and then the cube have to end over 2. If you take more than this, you go further than this, you don't get any new equations, because you get the conjugates of the previous equations. So you have to work with a set of all these equations, including the case k equals 1, which is the one of the previous example. So you have all this, and you have many examples now to work with. But first observe that these equations have a certain duality. Their equations, or the quadratic forms, are complementary. You take all the possibilities with all the powers of the roots of unity, and the examples are, I took one root of unity for one example, and the other example is the rest of them. The associated polytopes are also complementary. They intersect transversely in one point. And there's something more surprising. The polygon in the first case is the coefficients, is the configuration of coefficients. The polygon in the second case is the polytope, the associated polytope. And it also works for the polytope of the first case is the coefficient, the configuration of coefficients of the second one. So there's a very curious duality here. But there's a little asymmetry. In the second example, we know that it is smooth for all n, and for the previous one, it's smooth only for n odd, because if you have n even, you have one root of unity and minus the root of unity, and that is not smooth. So there's a very curious duality here. It's something one really wants to understand better. This is not the way we work, but this is joint work with Matthias Franz. But the way we work was, now we think that the way to proceed is to start with a simpler example, a simpler situation, complex varieties. So you take we take now the complex projective varieties with the same equations. You can also take any exponent in this case, and you take a primitive root of unity and you get a variety, complex variety, by taking a subset of the numbers 1 to n, and you take all these equations. This doesn't have, in special cases it will have dihedral symmetry. I won't go into this, but this one has cyclic symmetry. All of them have cyclic symmetry. And the first natural question is to ask when is this variety smooth. And in this case, it's not a question of weak hyperbolicity, but what is called in some contexts hyperbolicity. You take the matrix of the coefficients and you want to know that all its bigger minors are different from 0. Not just one, but all of them for a variety like this. This is called hyperbolicity. That's why the other thing is called weak hyperbolicity. Here you want I've just finished. Okay. So now the crucial question becomes, when is a minor of the van der Monde matrix with the roots of unity, nth roots of unity? When is it equal to 0? When it's not? It turns to be look like a simple question, but we couldn't solve it, and making experiments with big prime numbers like 23, we couldn't go any further. You have to compute many determinants, but it looks like for any prime number, then all the minors of the van der Monde matrix are non-zero. And we had we made another conjecture out of these computations that a minor is 0 even only if the complementary minor is 0. Well, but it took us some time, but we finally discovered that the first conjecture was a deep theorem that had been proved 90 years ago. It was conjectured by Ostrowski from a problem in partial differential equations, and there's a proof by Chebotariev involving algebraic number. I'm finishing. Algebraic number theory for p-adic numbers. Very complicated, but there have been other independent proofs. Was constructed, asked by a certain Morgensen and answered by Dieudonné in 1970, which a better, more understandable proof. And recently there was one by Terence Tao. I just mentioned the name of Tao's article. It's about cyclic groups. It's about has to do with this kind of applications. And encouraged with this, we looked for the proof of conjecture 2, and it was not very difficult. Just writing the matrix in a good way, and then applying a formula by Jacobi of minors of complementary minors of a matrix and its inverse, and we proved conjecture 2. Apparently, Tao and company don't know about this part. Maybe it will have applications for information theory and things like that. Connection of singularities with information theory. That would be good. Okay. Okay, so this clarifies the situation for the complex varieties. If n is prime, they're all the possible subsets of J give smooth, and if one is smooth, the complementary is smooth. Here the duality is not as rich because there's no polytope apparently, might be, but people look at this and they say things like, oh, it's mirror symmetry. Other people say it's Gorenstein symmetry. I don't know about that, but maybe it has relation with something else. Okay, so we get many more examples, and for the real case, okay, we're trying to go deeper into this because it's not, in the case n is composite, we still don't know everything. So we get, in the real case, we only need weak hyperbolicity, but hyperbolicity is even better, and we get a lot of smooth examples with dihedral symmetry. But since we need hyperbolicity, then weak hyperbolicity, which means that there are no convex combination of columns that give zero. So there are more possibilities, but on the other hand, things get very more complicated. And now, since it's weak hyperbolicity, the complementary, the dual of a smooth case is not as smooth, just as you said before. And we know a little bit about this, but there's a lot of things to be done here. So I think it's a very interesting question in which to work. And that's all. Thank you.
Are there any questions or comments?
Thank you, Santiago. Very nice talk. I think about equivalence may help to some questions like to say that for any generic pair of quadrics, the link is smooth, and small perturbations give topologically equivalent cones. If perhaps even Lipschitz equivalent cones, and that the links are infinite diffeomorphic. They don't say K equivalence, of course, doesn't help with describing the topology. And another question is, a nice class of examples seems to be pair of quadrics when you look at the Hermitian product of two linear vector fields, right? So it would be interesting to know if we have some particular type of topology for this class. Because you looked at this in a paper long time ago, no? I think.
Long time ago, Vinicio and I tried to look at the Hermitian forms. Maybe it's not really a Hermitian form.
Sorry?
Maybe it's not really a Hermitian form.
Hermitian product of two linear vector fields.
Yeah.
Hermitian inner product.
So here's the microphone. Did you hear anything I said before? Oh, I thought I had this microphone here. We'll talk about this, yes. For the first part, well, this weak hyperbolicity is generic, so we have always a generic smooth intersection for any number of quadratic forms that we have, and of course you perturb it, the thing is still, but the problem lies at the vertex of the cone. That's what I realized this week. Okay, so
another interesting application of results would be for the so-called generalized eigenvalue problem. This is a very interesting problem in applied maths, where instead of one matrix, you consider a pair of matrices. So if the two matrices are symmetric, then I think you can apply your result, and then you probably can say something interesting about that. But this is a very, very long problem in applied maths.
You tell me about it. I just must say that at the origin of Wald's normal form is this kind of operation. It's put in the generic case, so you can assume one of them is invertible, but the way to think about it is to take this generalized problem. The real eigenvalues correspond to the diagonal parts, the complex correspond to the other parts. So it's implicit in all this, in a sense. But yes, I would like to look at those other things.
Any more questions, comments? Okay, we thank you again.